to today's session focused on efficient AI technology. My name is Ling Liu. I'm a researcher from Cisco Research. Today, we have invited experts from various institutions discussing cutting-edge advancements. The purpose of this event is to delve into various innovations and strategies aimed at enhancing the efficiency of AI models across different domains. Let me outline today's agenda. Each speaker will have approximately 30 minutes, including time for questions. We will conclude with a panel discussion. Throughout the session, please feel free to engage with our speakers by posting your question in the QA chat box. Your questions and insights are valuable to enriching our discussion. Some introductions about the background of efficient AI research in our team. Our team has been working on efficient AI a couple of years and published multiple top conference papers in this space. In parallel with research, we are trying to contribute to open source community. We packed some of our research outputs into an open source software library called ModelSmith. Both threads keep evolving. We keep doing theoretical research and developing open source toolboxes. So why do we spend time and efforts on this research? And why do we need to make AI more efficient? The figure on the left shows accuracy comes at the cost of high computation. The size of the circle indicates how much number of parameters of the neural network. In the past, in order to chase accuracy, the size of the models are larger and larger. Large models need a lot of power and are not easy to use everywhere. The figure on the right shows the trend of the supply of AI computing and the size of large language models. The yellow line shows the computing capacity in modern GPUs, and the red line shows the model size and the number of parameters in these language models. The model size grows at a much faster rate than the hardware can offer. The gap will become larger, so we need to learn model compression technology to reduce the computing so that we can efficiently and make the future of AI more scalable. So far, ModelSmith has developed three main functionalities: pruning, quantization, and machine learning. Pruning and sparsity make neural networks smaller by removing synapses and neurons. The target of pruning is to reduce the number of weights, and the target of quantization is to reduce the number of bits per weight. Machine learning is a new functionality we developed this year. It requires the samples and their influence and be completely and quickly removed from a training data set and a trained model. These three figures shows the number of publications, and we can see the number of publications is growing super fast in the past few years. This demonstrates academia has realized the importance of efficient AI. And on the research side, we collaborate with several groups from different universities on efficient AI. For example, Professor Ling Liu and her team at Georgia Tech have conducted a comprehensive study on a novel early exit scheduling framework for multi-exit DNN models. And Professor Sijia Liu's research at Michigan State University focuses on data set pruning and machine learning, which we have already integrated into ModelSmith. At Purdue University, Professor Yung-hsiang Lu's team has addressed the latency challenges in vision transformer with their innovative approach. And Professor Elisa Ricci at the University of Trento focused on vision language model pruning. We are trying to integrate this work to ModelSmith recently. And we also work with UT Austin on graph mixture of experts and with IIT on post-training quantization. To summarize the project, ModelSmith is a toolkit designed to optimize models for deployment across diverse devices and platforms, ensuring satisfactory performance. And ModelSmith compress machine learning models. And ModelSmith leverage a wide array of technologies, including quantization, pruning, and machine learning to deliver versatile solutions. ModelSmith bridge the gap between the supply and the demand of AI computing. Let me show a demo to help you gain a better understanding.
Welcome to the ModelSmith demo. So ModelSmith is an app that serves as a toolkit for compressing machine learning models designed to enhance their speed, reduce their size, and improve the energy efficiency. So the first thing that the user is going to see as soon as he starts the app is the login screen. From there, he can start the app in two modes. He can go into the expert mode, a very configurable part of the app where he enters all the data, or guided mode where we will try to help the user to know what he wants to do. So yeah, let's go to the guided mode, and we have here a wizard, which is basically a set of questions which are going to help the user know what algorithm maybe he wants. Then he can just select it and click on run. If we go, for example, to the expert mode, the other type of mode for app, we can see here the same previous wizard that we just had, but now we can choose our own algorithm which we want. We can choose also the model for which we want. So let's say, for example, we want to run the IMP script using the ResNet 18 model with the, let's take the default parameters and let's click on run. This is because I had the previous script running. This is the command which we are sending to the VM. For example, the example is running IMP script with the parameters which we have configured and the model we just set here, ResNet 18. We can see it already started. Let's scroll to the bottom and it's running. When this algorithm is running, it's automatically generating also a chart, as we can see here. Yeah, this is basically all the data that we are seeing in this terminal being generated in this chart format. We have tooltips. We see that it already started the pruning phase, the epoch 1 I mean. Okay, it's going really fast. If we click here, we will stop it. And also another feature we have for the charts is, for example, the zoom. We can zoom in, we can drag and drop to view better what we want here. And at the end, each run, it's being saved in a history of runs. We have this feature called algorithm comparison, where, for example, for pruning, we can select the previous run that we had within our app and import it here in a comparison table. And for example, let's add another one. Let's add, for example, the IMP's ResNet 18, which was, yeah. Let's add it. Yeah. Okay, this contains a lot of data. Let's make it a little bit smaller. Let's zoom. So zooming, yeah. We can see, we cannot see that good because the color does not help us, but we have a fix for that because we can change the border color. For example, let's say we want a green color so we can better view the difference inside the table. Let's enable the zoom. Yeah, so for example, this is how the algorithm comparison works. We have here all the parameters. We can sort the tables, and the comparison can be made for quantization, pruning, and machine learning at the moment. Another feature that we have is the machine learning, where it's basically a machine learning script where we select a model, we set the parameters, and we click on run. As you can see here in the models panel, we have those which are selectable and those which are not. Those are not yet trained models that we need to train first in order to use them. And how we do that, we can click on the train models. It will take us to the model training page, and then we can select, okay, for machine learning, I would like to train the ResNet 50. I see even a history of this ResNet 34. Okay, it had just 2 epochs for 4 minutes. And yeah, just select and run for how many epochs, and it will just start the training. Another feature that we have here is the LLM quantization. So it's the activation aware weight quantization, where we can select this model from Hugging Face, and we can configure it, and we can click on run. So we can see that it's taking the auto AVQ paper. It logged into the Hugging Face, and it just started to run the code there, and we can see everything that's happening on the terminal. So that was it for the demo, and have a good day. Bye.
Which you can find on Cisco Open GitHub. We welcome contributions from individuals or groups interested in enhancing the project. If you have any questions, please feel free to contact us at research@cisco.com. Let's now begin our first presentation by Professor Elisa Ricci on efficient learning over multiple tasks. Elisa Ricci is an associate professor at the Department of Information Engineering and Computer Science at the University of Trento, and the head of research unit Deep Visual Learning at Fondazione Bruno Kessler. Elisa is also the coordinator of doctoral program in Information Engineering and Computer Science at the University of Toronto. She is an Alice Fellow. Her research lies at the intersection of computer vision, deep learning, and robotics perception. Please join me in welcoming Elisa. Please take over.
Hi, try to share my screen. Do you see my screen?
Yeah.
Hello?
Yeah, I see it.
You can see. Okay. Okay, perfect. Okay, thanks a lot for the invitation. It's always a pleasure to be with you. I was already with you last year. So, and today I actually to present a couple of works that are on the same topic. It's about efficient learning when we have to deal with multiple tasks in computer vision. One of these work is actually the result of a very fruitful collaboration with Cisco. So, sorry, okay. So, as you know, in computer vision, we've been dealing with multiple tasks. Tasks that goes from understanding and interpreting images at pixel level, localizing objects, so segmentation, detection, but also understanding the 3D structure of a scene, also being able to understand if two images are related, for instance, depicting the same monuments, so for geolocalization application, or for instance, depicting, understanding if two images correspond to the same person. That means for instance, re-identification. Lately, our community have also moved towards tasks that not only involve the visual information, but also involve text. So we have over the years more mature solution, for instance, for captioning and for visual question answering. And so how do we deal with multiple tasks? So this is a bit the topic of my talk today. Another thing that has happened in our community over the years is that we have increased the size of the model involved in video understanding, and so in visual content understanding. And so we were first focusing on convolutional neural networks, then transformers came, and now more recently we are interested in vision and language models. And so this, of course, has increased the size of the models, also their capability, the generalization capability, but still we have to deal with the problem of efficiency. So for the specific purpose of this talk, I would like to focus on two different scenarios. First scenario where we have to address multiple tasks, in particular multiple tasks involving language and vision at the same time, so in a kind of multitask learning setting, and this is associated to the first work that I'm going to present to you. And then the second scenario that I would like to discuss is that it's a continual learning scenario where we have data that come from different tasks over different times. And so we have this idea of the multiple tasks, but they don't occur at the same time, but they are occurring sequentially. But in both cases, the question that we are trying to answer with the two works that I'm going to present to you now is, what if we have to learn over multiple tasks, but also we want to take into account with special attention efficiency? So what we can do. So the first work that I'm going to present is actually the result of our joint collaboration with Cisco, and is a paper that we presented last week at CVPR. And the paper is called Multiflow, Shifting Towards Task-Agnostic Vision Language Pruning. So as the title said, this paper is focused on pruning. So we all know what pruning is, so we would like to remove a certain set of parameters from a model, but we also would like to maintain the similar performance of the dense model. So to obtain our prune model, we are typically using the original model and then some calibration data, and this will be used to obtain the prune model. However, we have different methodologies, different approaches for achieving pruning. So first approach is pruning at initialization. So we would like to estimate some parameter importance and only keep the top K. Then a second strategy that is dynamic sparse training. It's actually a strategy that is relevant in our work because it's the only strategy that was used when we started to work on this project for vision language models. In dynamic sparse training, we basically gradually prune the network parameter and devise a pruning schedule. And then there is a post-training pruning where we also update the unpruning weights, and the output of the prune model should be equal to the output of the dense model. As I said before, when we started to look at pruning for vision language model, we mostly found works for dynamic sparse training approach. In particular, what we try to study is a scenario where we have multiple vision and language tasks. And so a first scenario is that you have a dense vision and language models, and then you want to prune the VLM according to the task that you have in front. So for instance, we all know that vision language models can be used for several tasks, let's say captioning, vision question answering, retrieval. And so the traditional approach is that you decide the task that you want to address, and then you prune the VLM according to that specific task. And you can do that with an approach that exists. However, there are two main issues. So the main issue is that every time you change a task, you need to perform a new pruning starting from the dense model. And then another problem is that the dense model must still be trained. So the approach that we took to overcome this issue is illustrated in this slide here. So our research question is, can we address visual language model pruning in a task-agnostic fashion? So can we produce a model with reduced complexity that can be used for different tasks? And can we prune only once? And to try to deal with this new problem of task-agnostic visual language model pruning, we had to face two challenges. The first challenge is that we need a strategy that should be fast. And this is clearly not trivial. And the second challenge is that this approach should be task-agnostic. So we should be able to prune despite the downstream task, and therefore the pruning objective is unknown. So in the following slides, I would like to show you how we address both the challenges. Let's start with the first challenge, the challenge about speed. So can we prune fast? So as you may know, when we are dealing with pruning, we either require to estimate the gradients based on the loss, or we use some weight reconstruction approach based on second-order information. But in both cases, we have problems because these approaches are somehow time and memory intensive. When we started to work on this project, however, we found a very interesting work at ICLR that was showing somehow that for large language model, some valuable information for pruning already lies in the activation. So we took inspiration from this work. And then a second thing that we took into account to develop our approach is the fact that typically the saliency criteria that are used for a structural pruning only look at the parameters individually, so there is no structured information that is used. And we want somehow to recover the structured information, and these two principles, so the use of activation and the use of structured information, guided us to define this notion of information flow and to use this notion for our pruning approach. So what we propose is to compute the saliency of an input neuron by taking into account all the different subsequent neurons that are connected to a neurons, and then we estimate the saliency by taking into account the activations, the L2 norm of the activation, and the weights associated to the different connections. We perform something similar also for the output neurons, so we take into account the information that flows to this node here, coming from all the previous nodes, and similarly we compute also the saliency of the output neuron. Finally, what we are interested into is actually this, so is a saliency of the parameter that is connecting some input and output neurons, and this saliency can be defined by taking into account the saliencies that are computed for the input neurons and the output neurons and the weights. Which is the advantage of doing that? The advantage is that this approach is actually fast because it's basically relies only on computing the activation, and so it only needs some forward passes. This somehow addresses our previous issue, the first issue, so the issue about efficiency, but then there is another issue. I want a universal lottery ticket for my vision language model. I want to ensure transferability to multiple tasks. And as you may imagine, this is actually challenging because I can imagine that the different network can be used for visual question answering with respect to another downstream task that could be retrieval, for instance. So the question that we ask ourselves is, when we are pruning, which modality should we privilege? So the text or the image? And the answer is actually no one. So we actually need to put the priors and simply think that all the modality are equally important. And of course, this assumption is now, as I'll show you in a while, is implemented when we are creating our pruning masks. And this assumption is actually pretty much important to have the method working for different tasks. So these ideas led us to the second component of our multi-flow approach, that is multimodality aware compression. So here the idea is that I would like to compute the pruning mask with two intuitions. The first intuition is that there should be obviously some bias if I'm moving from a layer to another layer. And there is also a bias if I am going from one modality to another modalities. But then I want to somehow compute my, my pruning, to prune my weights by somehow removing both the bias related to the layer and the bias related to the modality. So somehow I would like to ensure a balanced pruning across the different modalities by respecting some global sparsity target. And this is somehow the intuition that led us to derive this formula and to implement some multimodal aware compression scheme. So overall, our approach, as I told you, is based on two components. So we call our approach multi-flow, so multimodal flow, because there is a first component that is this information flow that allows us to estimate the saliency associated to the weights. But then if you simply use the saliency of the weights to perform a pruning, that wouldn't work, due to the two bias that I mentioned before, the bias over the different layers and the bias over the different modality. So that's why we also need this multimodal aware compression scheme to ensure that we have a network that is well proved. So very quickly, what about our results? So here, for the sake of, due to lack of time, I didn't show you much, but I just have a couple of tables, but actually our evaluation is pretty extensive. So we considered multiple vision language models, and we consider multiple tasks. In particular, in this slide, I have both image text retrieval, image captioning, and visual question answering. With, of course, associated data sets. And what you see in these tables is that independently of the VLM that you are using, our approach beats the state of the art that at the time was an ICML papers, and also it's on par to this method for the other two tasks. However, our approach is much, much faster than the second best performer, and also we are extremely good in terms of memory required. Other interesting things that we discovered are somehow in this plot. So the first thing that we discovered is that actually, as it was somehow reasonable, if you move across the different layers and across the different modalities, the activation are very different. And that means that also the saliency will be different. That means that we may have some situation where we have some modality collapse. And somehow the constraints that we are putting on multi-flow when we are pruning allows to avoid this modality collapse. Another interesting thing is that we ask ourselves, what happens if we are very extreme in pruning? So what happens if we are requiring like 90% of sparsity? And somehow I think that multi-flow is pretty much robust with respect to previous approaches when we are requiring a significant, significant sparsity. For instance, for image captioning, we have a quite good Blaze score. So to conclude about this first work, so we decided to explore for the first time this idea of finding a universal lottery ticket for VLMs. We have two primary contributions. We introduce our new approach that is specifically designed for this purpose, our multi-flow. And then we had another contribution is that we perform a very systematic evaluation of our approach and different methods on different multimodal tasks, on different VLMs. And I think this could be useful for future work on the same topic. Interesting finding also come from this additional analysis showing that VLMs can be indeed pruned with very high sparsity, and also that one thing that we have to take into account when we are pruning with VLMs is that we may have some issue in modality collapse. It will be actually very interesting to see how this translates when we are considering, for instance, more modern model or models that contain different type of modalities. The second work that I'm going to present to you, it's about another topic, but it's still focusing on efficiency. So here we are focusing on continual learning, and in particular on multi-label continual learning. And we have this idea of summarizing the patch tokens in a transformer for efficiency. So we have a different setting here. We are in continual learning. As you may know, in continual learning, we want to learn models from different streams of labeled data. And we would like that when we are learning on new tasks, we don't forget what we have learned before. So we want to counteract catastrophic forgetting. In particular, in this work, we were interested to a particular scenario of continual learning that is a class incremental learning. So in each task, we have a set of unique classes. In particular, here we are focusing on multi-label classification. So we have different labels. And then at test time, we don't have any indication of the task. So no task ID information is provided at test time. This, of course, makes the inference more challenging. So multi-label class incremental learning is actually much more interesting and much more difficult than classical class incremental learning. And the main reason is illustrated in the slide that you see here. So when you are interested in counteracting catastrophic forgetting, catastrophic forgetting is actually much more pronounced when you are in a multi-label setting, because the classes that are in the not annotated for a certain task, but are in the foreground, but that you have seen only in the previous task, will lead to an exacerbation of catastrophic forgetting. Another issue is that since you have several labels, you are also facing the problem of long tail distribution. One additional issue is the fact that the state of the art in when we started to work on this project were for class incremental learning were prompt tuning methods. However, if you applying prompt tuning method to multi-label class incremental learning, it's non-trivial. Because if you have multiple classes, somehow selecting the correct prompts also corresponding to different from ground object could be not very trivial. So the method that existed previously then to our work were actually not prompt tuning methods, but were method based on rehearsal. However, in this work, we demonstrated that actually prompt tuning can be used with success for multi-label class incremental learning. So what we propose? We propose to address this problem with a parameter isolation method. That means that we have task-specific parameters for each task. In particular, the architecture that we propose is the one that is illustrated here, where you are basically having a frozen backbone and then some task-specific parameters for each task. So this is a kind of multiple pathway architectures. So we are training a set of parameters for each incremental step, but then we are also using all the trained parameters at inference time to make the prediction. As you may imagine, this approach doesn't scale when the number of tasks grows. So in order to limit the computational requirements and to achieve efficiency, you need to be smart. And what we propose is we propose to summarize the internal representation of a visual transformer for each different pathway. In this way, each forward pass will be very cheap to compute, and our approach can scale to a large number of tasks. So how do we achieve this summarization? We introduce this notion of trainable tokens that somehow serve the purpose of selecting a set of patch tokens. So they are somehow some patch selectors. And so what is happening, and this is illustrated here, that from the original patch tokens, we are learning some patch selector and we are performing some summarization, and then the summarized patches will be used for prompt tuning, making the prompt tuning much more efficient. This is an expansion of the architecture that we propose, that we call multi-lane. So we have first common forward on the frozen visual transformers. And then this is the original part of our approach, where, as I told you, you have some patch selectors, and then you are creating some summarization. And the summarization is illustrated here, where we are basically computing some importance weights associated to the different patch tokens. And then the output of this summarization is used in the multi-head attention, making this order forward much more efficient. Interestingly, while different methods for continual learning also make use of additional losses, for instance, distillation losses for interacting forgetting, our approach, being a parameter isolation method, is only trained with a binary cross-entropy loss that makes the approach pretty valuable and interesting. This was a bit the idea of our method, and then maybe some results. So when we, at the time of our submission, the best method was this KRT method. That was a method that works quite well, but it works especially well when you have a huge buffer size. Our approach, instead, being a prompt tuning method, doesn't employ a buffer, and despite that, is actually much more achieve much better performance than previous methods. Then a slide that I don't have here is that it's true, we conceive our method for a multi-label classification, but actually our method is also competitive with other prompt tuning methods like Coda prompt, even in a scenario where you are not in the multi-label setting. An interesting visualization of what is happening with our patch selectors is shown here, because basically when we are producing this summarization internally the transformers, basically we see that when we arrive to a certain layers, some concept naturally emerge, despite our transformer is now pretty efficient. So for instance here, that you see that the concept chair is clearly individuated, and you have here. And you see that here, for instance, the concept skateboard is also very well found. Going into efficiency, we also evaluate our method, and we saw that this idea of the patch selectors is actually very competitive with the state-of-the-art methods. For instance, with token merging is actually better. And also another interesting thing that we found is that even if you employ few selectors, like 1 or 2, then our approach is still very competitive, and enough information can actually be encoded even if we are using a single summarization patch. So to conclude about this work, so we show this new approach for multi-label class incremental learning. This approach is called multi-lane and achieve the state-of-the-art in multi-label class incremental learning. We introduced for the first time into prompt tuning methods this idea of patch selectors, because we want to efficiently summarize the VIT internal representation. We show that our patch selectors reduce computational requirement. And of course, now we want to move, as in the previous work, into multimodal models. And we will also like to move beyond classification, maybe towards the segmentation, and see if we can actually build a multi-pathway efficient architecture for semantic segmentation. So this somehow concludes my presentation. Thanks for your attention. These are the 2 papers. So one paper is just released, where there is also the code available. And also for the second paper, the code is available, and we are going to present this work in the conference on lifelong learning in the next month. Thanks for your attention.
Thank you, Elisa, for your insightful presentation. And I have a question for the first work. I'm wondering if different modalities have different pruning ratio, because I think different modality may contain different type of information. and the density of this information may be different. And it is possible for a certain modality you can prune more aggressively than the other modality.
So the reason why we didn't do that is because we wanted to have an approach that is task agnostic, and we wanted to see how far you can go if you don't put any of such constraints. Of course, I guess, this notion of information flow can be also combined with the other eventual strategy. Maybe this need to be studied also, as I told you, as I was saying at the end of my presentation, also for other applications. So I'm saying we are not done. This was, let's say, a first exploratory works to see how far you can go into this task agnostic direction. Another interesting thing for me is actually also to have better ideas for being task agnostic. So when we started to work on a project, we were also thinking about importing other notion, maybe from, domain generalization, like literature and something like that. So even there, we are not done. It was a first work. It's actually a method that is pretty simple and it's quite effective despite the simplicity. But of course, we don't believe we are done with this project. There are a lot of things that can be tried. And as you may imagine, by the time we work on this, now there are much more multimodal models that we can play with. So I would say that there is a lot to do, definitely a lot to do in different directions, different modalities, different pruning way to handle this pruning ratio, different applications. So it's really just a small seed, right?
Yeah, I believe vision language multi-models is a very hot topic, and we can explore more in this direction. And for the second work, I just have a short question. So how to define different tasks? I didn't get that.
Yeah, that's something that in this work is actually not something we have introduced. So this is classical setting in multi-level class incremental learning. So in class incremental learning, basically for each task, you have a different set of categories. In the multi-level setting, this is the same idea, but expanded to the multi-level settings. Of course, there are also other settings. In this work, we specifically focus on the multi-level thing for the reason that maybe was not so clear in my presentation. So I want to rebound on this. So the state of the art in classical class incremental learning is this prompt tuning approaches. However, people found very hard to scale this prompt tuning approach when you have multiple categories or when you are in a multi-level setting. So we wanted to demonstrate that this is actually possible. But the setting is that. Then, of course, this is still recognition, okay? Now we have a forthcoming work that is for actually continual learning and visual question answering that we are planning to submit to VACV. So we are also in this continual learning scenario, we are now moving to more complex language and visual tasks. This was a still recognition and single modality work.
Oh, I see. This is also a very interesting work. And thank you again for your impressive presentation. And next, we have Dr. Sijia Liu from Michigan State University. Dr. Sijia Liu is currently an assistant professor at the Department of Computer Science and Engineering, Michigan State University, and affiliated professor at the MIT IBM Watson AI Lab, IBM Research. His research spans the areas of machine learning optimization, computer vision, signal processing, and computational biology, with recent focus on trustworthy and scalable ML. He has published over 60 papers at the top-tier ML AI conferences and organized and co-organized several tutorials and workshops on trustworthy AI and optimization for deep learning at KDD, AAAI, CVP, and ICML. Professor Liu will share his research on Zeroth-Order optimization for memory-efficient fine-tuning of large language models. Please go ahead.
Okay. Great. Thanks for the work and introduction. Hi everyone, I'm Sijia. Today I'm going to ask one question about large language model fine-tuning is how can we reduce memory? So as we know, the large language model fine-tuning is a memory killer, right? You have to use some very advanced GPUs, even multiple GPUs, to fine-tune normally use a large language model. However, the question is, can we reduce memory so that we can adapt the fine-tuning task on low-end GPUs? So I'm going to talk about one technique which is called Zeroth-Order automation. The Zeroth-Order, you can think about it as a reduced version compared to first order, but there's an advantage. This key advantage is you don't need to use gradients. You can only use for the past to estimate gradients. And let's get into how these ideas can help us to reduce memory and achieve the memory efficient fine-tuning for large language models. I give a very quick introduction about this is a Zeroth-Order automation technique before we integrating this to large language models. So as I said earlier, what's a Zeroth-Order automation? Basically speaking, it's a gradient-free automation technique. Then we are trying to estimate the first order gradient using the finite difference of the function values. It's pretty simple. You can think about things, we only use the function values to estimate gradient. Therefore, this Zeroth-Order automation can be used to solve many black box machine learning problems, or in some problems achieving gradients. For example, using BP in the deep models is very expensive. And clearly, there are some advantages, right? If we can use function values to estimate gradient, and suppose the gradient estimation is accurate enough, then we do not have to rely on the first order gradient method, and we can just use this gradient estimation to update the model parameters. For example, if we want to do the fine-tuning task, it's very simple and easy to implement. You just replace the first order gradient with this finite difference based gradient estimator. And in theory, there are also several very good properties for the Zeroth-Order automation compared to traditional derivative-free automation methods. For example, and people have found that the Zeroth-Order automation can be provably converted compared to some other methods like Bayesian, like genetic algorithms. And even the convergence rate is slower than the first order method, but still it's a provable convergent. And meanwhile, there are some challenges for using Zeroth-Order automation. I will show this later, but generally speaking, so convergence is very slow. And how to speed up this Zeroth-Order automation approach, and so that it can adapt to the large language model fine-tuning applications. This actually is non-trivial, it's very challenging. And also how to scale up, like how can I leverage this Zeroth-Order automation to solve these large scale problems. When the variables that you want to optimize is high, the dimension is high, then this is also very challenging. So in the context of the LLM fine-tuning, I will show this later. These two challenges can be solved relatively leveraging some good properties of the pre-trained large language models. So I give very simple examples. Try to compare this as a first order method versus a Zeroth-Order method. And you can think about, regardless of the first order or Zeroth-Order method, we are trying to solve an automation problem. You have some automation variables, let's call X. You want to minimize loss functions, Fx can be given by the empirical risk loss given by the sample or the training samples. But the key problem for this problem is we assume that this function is a black box function, which means we can think about this black box function, we cannot conduct a BP over the models. And you can only query this model. You can think about this model as a language model as surveys, or as a vision model as a surveys. And this N here is a number of training data points. If this image, then it's a number of training images in the training set. And the Zeroth-Order automation trying to solve these problems, as I said, trying to estimate gradients of these loss functions using function evaluations based on the finite difference of the function values. And the estimator is very simple. It's actually derived from the concept so-called directional derivative. So the key idea is you are trying to pick a random direction. That's called U. And this U typically follows a standard Gaussian distribution. You pick a random direction, and then you perturb the variables x. This is the variable you want to optimize. And then you calculate the difference of the function values before and after perturbations, and divided by the perturbation step size beta. And this is a function difference. This is known as directional derivative for the following the direction u, and you times this direction u. This gives you the directional derivative based weighted estimator. But this estimator is it seems very simple, but it's very powerful. You can prove that this estimator is good enough for the low dimensional case, but still in the high dimensional case, this gradient estimator will give you some errors. But generally speaking, for the Zeroth-Order method, you just replace this is the original first order gradient with this gradient estimator, only based on function values. And you replace this gradient with a Zeroth-Order gradient estimator, and then conduct the standard the alternation measure like SGD and do this alternation for this variable x. But one thing I want to give a remark is this gradient estimator using the function values, generally speaking, is not an unbiased estimator. It's a biased. And also it gives us some large variance. So therefore, how to reduce the bias, how to reduce the variance for this Zeroth-Order gradient estimator, and so that we can use it for the deep learning applications. It is a challenging task. But from the automation perspective, you can think about this is the first order versus Zeroth-Order. They can all convert into some solution, but the difference is the first order method converts very fast. And the conversion rate, typically it's a sublinear rate. It's a 1 over square root of t. And here t is the number of iterations. This is for SGD. But for the Zeroth-Order version of the SGD, it also converges, but the convergence is relatively slow. And the reason is the gradient estimator is not accurate. It's a bias estimator, as I mentioned. And this directions is a little bit random compared to the first order gradient. And you have to pay a lot of iterations until on average it will converge. So it can be proved that the conversion rate is also guaranteed. But this convergence will suffer from a slowdown effect based on the dimension of the problem. And here D is the number for the alternation variable, so the problem size. That means if you use a Zeroth-Order method to solve a large-scale problem, then this has become difficult because this dimension of the variables could be quite large compared to the number of iterations you can run. So how to reduce the dimension effect, this is slowdown effect, and so that we can adapt this Zeroth-Order methods to the LLM fine-tuning task. That's a one key task that we will address later. So now we should ask the question, why should we care this is a Zeroth-Order alternation method? And as I said, the original motivation for us in the LLM context is we want to reduce memory, right? And think about what's the main advantage of the Zeroth-Order alternation. So the one advantage, as I said, is Zeroth-Order alternation can be used for solving the black box problem, which means the gradient information is infeasible to obtain. And actually, there's a lot of applications in that scenario. Let's, for example, in the adversarial machine learning context, in the simulation coupled machine learning, even for the model explanation context. But today we will focus on another scenario, which means even you can obtain gradient information, but the gradient information is difficult and expensive to obtain. And this is the cost can come from the memory perspective. I will show it later. And this difficulty has also been seen in many other applications, for example, meta learning, for example, on-device training. But today we will mainly focus on the memory efficient fine-tuning for the large language models. And so now let's talk about a bit more about Zeroth-Order alternation for the LLM fine-tuning. So we know that to fine-tune the large language models, we have a primarily efficient fine-tuning method we can use. But the primarily efficient fine-tuning does not mean memory efficiency, right? Because you only reduce the number of parameters that you need during the fine-tuning. But you still need to conduct the backpropagation to find this is a gradient with respect to those parameters. And during the backpropagations, it introduces the activation memory, which means you have to memorize the activation during the BP, and that actually costs a lot of memories. So let me give you examples. So let's just look at the fine-tunings, which can take forced order alternation, which is BP-based, and compare to several different forced order methods. And generally speaking, suppose we want to fine-tune this OPT 13 billion models on this is a multi-RC dataset. And we do the different primarily efficient fine-tuning measure. Like full fine-tune, this is not primarily efficient. This is just a standard fine-tune the large language models or the end-to-end fashion. But prompt tuning is a very primarily efficient fine-tune. It's very primarily efficient fine-tuning. It's very primarily efficient as you only inject the prompt to conduct the fine-tuning task. And prefix tuning is similar. LoRa is another low-rank matrix-based primarily efficient fine-tuning method. For those primarily efficient fine-tuning methods, let's look at the inference time. So the inference time basically only takes 25, about almost the same because of forward pass. It only takes about 25 memory cost. Here, the unit is the GB. But compared to the SGD, which involves the BP backpropagations per iterations, as you can see, the memory cost becomes 98. And for the full fine-tuning and for the other primarily efficient fine-tuning, it takes 92. And similarly, the ADAM even takes a higher memory cost because ADAM, which uses the so-called adaptive learning rate and the momentum to speed up and stabilize this alternation process during the model training. So therefore, it takes even higher memory cost. And one thing you can notice that even we can see the primary efficiency, like LoRa, like prefix tuning and prompt tuning, but the memory cost for the forced order method is still huge, and compared to the inference cost. So in briefly speaking, the fine-tuning that you have to take a BP that actually introduces a high memory overhead. It's 3 to 10 times more cost than for other paths. And this is the memory cost will change based on the choices of the forced order optimizer. The one issue for calling this memory cost is the optimizer has to rely on BP. And BP has to memory a lot of activation memory, has to take a lot of activation memory. Therefore, and zero-order alternation can play a role to reduce memory if we can avoid BP. So this is a key motivation that we can integrate a zero-order alternation and to reduce memory and to conduct model fine-tuning. And before we talk about zero-order alternation for fine-tuning large language models, I want to mention that there are also some other derivative-free or gradient-free alternation methods and in the alternation community. But we will not use them for fine-tuning large language models. There are several reasons. So for example, in mathematical programming, like there's several methods based on search, based on filter region. So those methods are very traditional zero-order or derivative-free alternation methods, but they are not very suitable for deep learning applications. The key issue is about scalability. And there are also some other methods like genetic algorithms, evolutionary alternation, or the Bayesian alternation. And they are also not very suitable for fine-tuning large language models because you have to build some additional models to conduct this alternation task. For example, the Bayesian alternation, you need to build the Gaussian process, the Gaussian models to estimate the mean, to estimate the variance, to find the solutions for the alternation problem. It takes a lot of efforts to build an optimizer that's suitable for the LLM fine-tuning. By contrast, the zero-order alternations, as I motivated early, is very simple. You just need to replace the forced order gradient with a zero-order gradient estimate. Then that's it. You don't need to you don't need to change much about this alternation framework that you have used for fine-tuning large language models. You just change the gradient estimator, and that's it. So that's why we focus on this is a so-called Zeroth-Order alternation, and which mimics the first-order method, but compared to the other types of the derivative-free alternation method, it's much simpler. So now even within this is a Zeroth-Order alternation community, there exist many different types of the Zeroth-Order alternation methods. As I said, the key component in the Zeroth-Order alternation is trying to estimate gradient using the finite differences of the function values. Like here, you draw the random direction, and then you take the finite difference of the function values, and then you times this random direction. That gives you a very simple, just 2-point based gradient estimator. And based on the gradient estimator, you can plug in this estimator into many different type of first-order methods. Then you will get the Zeroth-Order versions of those first-order methods. And here I give you a few examples. For example, you can use this Zeroth-Order gradient estimator in the SGD framework. Then you get a Zeroth-Order SGD. Similarly, you can get a Zeroth-Order sum-based SGD, which means you only take the sum of the gradient estimator as a descent direction. And also you have the Zeroth-Order SGD based on the momentum, and also Zeroth-Order SGD conservative versions, which means you also use some additional tricks to find the better learning rate, and also Zeroth-Order version of the item. So there's many different versions of Zeroth-Order measures. They are obtained from the first-order measures. The only difference is you replace the first-order gradient estimate, the first-order gradient with the Zeroth-Order gradient estimate. So it's very simple, but the issue is, as I said earlier, the first-order gradient estimate typically is unbiased. But the Zeroth-Order gradient estimator, which uses function differences, which is typically biased estimator. So we need to reduce the bias so that it can adapt to the fine-tuning applications. And in addition to those Zeroth-Order methods, I also want to mention another method that people also used for deep learning applications which does not require BP. So this method called forward gradient. So forward gradient is not a Zeroth-Order method, but it's BP-free. And the key point of the forward gradient is instead of using the finite difference of the gradient estimator, you are using the directional derivative directly, the precise directional derivative, to estimate the first-order gradient. And this is an unbiased gradient estimator, but it takes a higher memory to get it. And all of these gradient estimators and their performance in the large language model fine-tunings have been reported in our recent SML paper. And if you are interested, you can feel free to refer to that paper. So given this background, let's think about how we can integrate this Zeroth-Order alternation for LLM fine-tuning and reduce memory. So as I said, the large language models are very different from the many deep learning models. The key reason stays as a pre-trained phase. So typically, we fine-tune the large language models based on the well pre-trained models. And from the alternation perspective, the pre-training has enabled us to work on a well-optimized Bayesian of this as a solution. So which means, different from training from scratch, the pre-trained model already provides us a very good initialization of this Zeroth-Order alternation. So even we use this very cheap the finite difference the gradient estimator in the Zeroth-Order alternation regime, but we are working on a well-trained model. So in that case, even the quality of the estimator, the gradient estimator is low, but since the pre-trained model already provides us a very good high-quality alternation Bayesian, therefore, the integration of this is Zeroth-Order alternation for LLM fine-tuning becomes possible and even effective. As you will see the results later. And there's a second reason that we can integrate Zeroth-Order alternation for LLM fine-tuning. This is the so-called task alignment. So as you may know, the LLM fine-tuning and LLM pre-training, they can be aligned using a single task, which is called token on next sentence prediction. So for example, even for the classification task on the fine-tuning phase, you can rephrase the classification task using additional prompts, and so that it makes you customize this classification task as a token prediction or sentence prediction task. So due to this alignment nature between pre-training and fine-tuning, You can further simplify this fine-tuning task by rephrasing any like prediction task as a token prediction and sentence prediction task. So what's the benefit? The benefit is since you align this fine-tuning task with the pre-trained model, therefore it will facilitate us to use this Zeroth-Order alternation. Since this Zeroth-Order alternation will be no longer considered for the task transfer case. You are working on the similar task types during the fine-tuning compared to the pre-training. And this Zeroth-Order alternation can better utilize these pre-trained models to find a better fine-tuned solution. So this task alignment is very important. I will show one examples tell you why this task alignment plays a role for the Zeroth-Order alternation in the fine-tuning of the LLMs. So let's consider a very simple task, which is we use even not large language models, as remote large models. And we consider battery classification task, which is SSD2. And if you look at the SSD2 task, and with task alignment, here is highlighted by this is a checker marker. And without a task alignment is a cross marker. As you can see, for the first order method, even without considering the task alignment, and you can achieve a similar performance for fine-tuning. But for the Zeroth-Order method, you have to consider task alignment. Otherwise, the fine-tuning performance will degrade significantly. And how to achieve task alignment? As I said, since large language models allows us to use prompt. So we can reframe this is a battery classification task as prompt sentence prediction task. You can just ask, is this true or not? Then it's just predict, it's just answer true or false. It behaves as a classification task, but from the loss perspective, it becomes the next sentence or next token prediction task. So once more, this task alignment that allows us to reduce the gap between pre-training and fine-tuning, and reducing this gap will make the Zeroth-Order alternations becoming more effective in fine-tuning large language models. And as I want to highlight, with task alignment, you can, as you can see, we can achieve the over 10% or 80% accuracy improvement compared to the standard Zeroth-Order alternation without task alignment. And if we move to more models, instead of a robot larger, you can consider other models like OBT model, like Llama 2 model, like Vicuna and Mistral, and all those models. We can use the Zeroth-Order alternation to fine-tune on a series of tasks. And from the very simple tasks SSD2 to the more complex tasks like multi-RC, and all of those tasks can be effectively conducted using Zeroth-Order alternation. So I will introduce the results later, but here I want to emphasize we consider the full fine-tuning measures, as I mentioned earlier. One is the full fine-tuning, and 3 other fine-tuning measures are primarily efficient fine-tuning measures like LoRa, the prefix fine-tuning, and prompt tuning. And I want to highlight a few messages from the experiment results. And first of all, if we look at the family of the Zeroth-Order measures, and if we consider a simple task, like easy task like SSD2, and then as you can see, the Zeroth-Order items typically behaves most effectively to maintain the fine-tuning accuracy compared to the first-order method. And even sometimes in like prefix and prompt, those primary efficient fine-tuning regimes, and the Zeroth-Order method can match the first-order performance, and even sometimes it's slightly better. And the reason is the Zeroth-Order method is a stochastic, it contains a stochastic noise. Therefore, its performance could even outperform first-order method in some scenarios. But generally speaking, the Zeroth-Order method is only typically only comparable to the first-order method. And like if in the full fine-tuning context, you can see the Zeroth-Order method typically is lower than the first-order method, but it's very close. So this gives us a very positive sign about the effectiveness of the Zeroth-Order method. We only use the function queries to estimate gradient, and use that gradient to fine-tune the models across the different fine-tuning schemes. And for both robot large and OBD 1.3 billion models, and it works very well. And why zero-order item is the most effective? Because the items typically use the adaptive learning rate and some additional momentum strategy to stabilize this is automation process. And the similar advantage also holds for the zero-order methods. And that's the one reason the zero items behaves much better compared to other methods. And another interesting observation is if we look at the forward gradient method, forward gradient method does not always show significant advantage over zero-order methods. As I said, forward gradient is using unbiased gradient estimator, but does not rely on BP. However, in this fine-tuning context, forward gradient does not show significant advantage over zero-order methods. There could be several reasons. The first reason is the current task is simple. So as I said, fine-tuning plus task alignment has well-aligned fine-tuning task with pre-trained task. Therefore, it's not a difficult task. Consider this downstream task is SIG2, it even becomes simpler. So therefore, forward gradient does not show promise compared to the zero-order measure. And later on, I will also show that forward gradient is also not memory efficient compared to zero-order measure. And moreover, if you compare the simplest method like zero-order SG sum, which is only use sum of the gradient estimate to update this fine-tuned models, and you can see the zero-order SG sum method typically not work well. So therefore, you can conclude that we have to use the gradient estimate values instead of the sum to estimate to fine-tune the large language models, even for this very simple task. And if we move to more complex tasks, if we compare these different fine-tuning measures, it seems that LoRa typically behaves robustly when integrated with the zero-order alternation measure to fine-tune large language models. For example, in this OPD 13 billion models on two downstream tasks, COPA and Winogrand. And it looks at LoRa behaves very stable using this as a different zero-order measure compared to the first-order measures. And for the full fine-tuning measure, as you can see, the performance varies based on what measure you used in the zero-order alternation context. Right. And also, there's if we move to the model architecture, for example, you can use this zero-order alternation-based fine-tuning measure to fine-tune other type of the language models like Llama 2 and Vicuña models and Mistral models, and the performance seems very similar, and the conclusion also consistent with what we have observed for the OPT models. Generally speaking, very surprisingly, the zero-order methods can achieve very comparable and very close performance compared to the first-order based fine-tuning method.
Sijia, we have 2 minutes left, maybe.
Oh, okay, yeah, almost done. And if we move to the memory efficiency analysis, you will see that the zero-order method only takes single GPUs to conduct this fine-tuning task. The memory cost only takes 29 GB, comparable to the forward pass. It's not surprising because zero-order method only takes the forward pass as a memory cost. And if we consider this memory efficiency versus the input length, and this memory efficiency become more significant if we consider the long length text scenario for the large language models. And the quick summary, this zero-order method can demonstrate the advantage over first-order methods. And if the models itself very large, which means first-order method will take a high memory overhead for fine-tuning. And also, if you want to learn more about this zero-order alternation for memory efficient fine-tuning, feel free to refer to our SML papers, and also there are some other materials you can read for recent clear papers. And lastly, I want to thank my students to work on this project and the support from Cisco and NSF. Thanks.
Thank you, Professor Sijia. This is very impressive work. I have one short question. Is this algorithm generalizable to other models? Because I see it's, in this paper it's for large language model. I'm not sure if it's generalizable to other vision models.
Right. We tried on vision models. Unfortunately, it does not work well for the vision model. So there's a key reason. The reason is on the task alignment. For the large language models, you can always customize the fine-tuning task as token prediction or sentence prediction task, like QA task. But for the vision models, typically, we do not have such freedom, right? So that's one reason. So for using the zero-shot alternations, you have to make the fine-tuning task simple enough. And the pre-trained models plus, this is a task limited nature for the large language models, makes a zero-shot fine-tuning possible. But move to the vision models, unless we have the vision foundation models, that we can, the vision models can behave as a LLM, then that's possible to adapt to the zero-shot method. But so far, we do not have such a good nature for the vision model.
I see. That makes sense. And thank you again, Professor Sijia, and for your enlightening presentation. Next, I would like to introduce Professor Yung-hsiang Lu from Purdue University. Yung-hsiang Lu is a professor of electrical and computer engineering at Purdue University. He is a university faculty scholar of Purdue University. He is a fellow of IEEE, distinguished visitor of Computer Society, distinguished scientist, and distinguished speaker of the ACM. His research area include computer vision, embedded systems, cloud, and mobile computing. Today, he will be sharing his insights on computer vision for edge devices.
Thank you.
Please go ahead. Yeah.
For the introduction. Thank you for inviting me to speak here. Today, I will talk about our work on computer vision for edge devices. More specifically, we will talk about how to make transformers more efficient in the context of task specialization. So the previous speech talks about large language model. Now we are looking at a somewhat different kind of task. More specifically, we look at computer vision. Many tasks for computer vision need to be processed at edge devices. For example, you may have a drone that is flying that will require to do the processing on a drone, usually because it may fly in areas where there's no wireless network. You may also have situations where you have wearable devices, such as this example for inventory management, as well as situations where you have mobile robots where the latency is very important. A common question about efficient computer vision at edge is, can we simply send all the data to the cloud? There are many cases where this is not possible or not desirable. First, you may not have good wireless connection in specific areas. And also some of the tasks may be time sensitive, and you don't want to send your the data to the cloud, waiting for the processing and get the result back when the latency is unpredictable. Also, based on a study by Cisco, the internet is already very congested for many different kinds of video traffic. Then another important reason is you may want to protect privacy or security. Then in the previous example, if you do inventory management, you may not want to share your company's inventory with cloud because the data may be leaked. So for these reasons, we very often want to do computer vision on edge devices. In this presentation, I will talk about two methods on how to make computer vision more efficient for edge devices. The first is basically the concept is called token removal. We want to remove unnecessary information from the computation. And the second is a new way of designing the neural architecture. So these are two different methods. The first method is we want to reduce the latency of a vision transformer with token removal, but we also consider hardware characteristics. First, let me explain what's token removal. Suppose you have images like this as your input. You may have a car, you may have a Statue of Liberty. Then after some processing, you can remove some of the tokens. For example, for the Statue of Liberty, if we want to focus on the statue, we can remove the tokens representing the skies. The main question includes two parts. The first part is, how do we know which tokens to remove? The second question is, after removing these tokens, how much accuracy will be affected and how much latency will be affected. So the problem we want to solve is the following. We want to remove token because in computer vision, very often we have a lot of redundancy, as we can see in the previous pictures. The pixels for the skies are not necessary for recognizing the Statue of Liberty. And also, many existing methods for efficient transformers are not designed for pre-trained models, and the existing methods usually require training. Training is undesirable as training becomes more and more expensive. As Gowen said in the introduction, that the model gets bigger and bigger, training becomes very expensive. So we want to see how we can use pre-trained models to improve the efficiency. The second observation is most existing methods are not considering the hardware characteristics. So our methods will consider these two factors in the design. Why do we want to remove tokens? For computer vision, usually we will divide the pixels into patches, and the patches will form tokens. Then the tokens will go through the neural networks and be processed. If we reduce the number of tokens, then we can reduce the computation time. It is important to notice that in the current popular models for transformers, the computation time is quadratic function with the number of tokens. That means if we double the number of tokens, the computation time will become 4 times. Therefore, removing tokens can have very significant impact on reducing latency. There are 3 common methods for token removal. The first is called the token pooling. The second common method is called token merging. Basically, we combine different tokens into fewer tokens. Then the third is called token clustering. We'll take tokens and transform them in some ways to reduce the number of tokens. A common observation is the following. As we increase the number of layers, this is examples of a dyno, the computation time will increase linearly. This is not surprising because the more layers we need, the more computation time we need. However, there is also another observation is if we remove tokens early in the processing, then we can save more time. So if we remove more tokens early, then we can reduce the latency. However, if we remove too many tokens early, then the accuracy will suffer. So the challenge here is how do we balance between accuracy and latency. Very often, most work do not consider the characteristics of hardware. This is observed in many edge devices. That is, the number of tokens reduced, then the computation time can have a nonlinear effect in reduction. In this particular case, if we remove a few more tokens, we can have a significant reduction in the latency. This is a very important observation because of hardware characteristics. This is commonly called the tail effect for GPU. We have a paper pending, review pending. We are waiting for the result. The paper has 2 major contributions. We believe we are the first to decide token pooling methods based on hardware characteristics. And also, our method is training-free. We do not require additional training, and we can use our method in existing pre-trained models. The advantage of this method is that we can adapt our method in many different pre-trained models. In particular, for the recent popularity of pre-trained foundation models, we could apply our method to those models. This is the basic concept of our approach. Our approach is divided into 2 parts. The first is the offline computation. We decide how many tokens will be removed and what's the effect. We consider a state-of-the-art existing vision transformer. Then we measure the latency and the accuracy based on the different number of tokens. It is important to notice that the latency measurement will be specific to the particular hardware I mentioned. Then we determine, at the runtime, we determine how many tokens were removed based on the information available from the tokens. we propose a method that will consider the utility of accuracy as well as the utility of latency. So the utility defined as the accuracy divided by the maximum accuracy we can observe by the best ECT methods. In terms of latency, we want for accuracy, the higher is better. For latency, the lower is better. So it is 1 minus latency divided by the maximum latency. We also use conservative methods. We will calculate the accuracy using random token removal. The reason is this will be the lower bound of the accuracy because when we remove tokens randomly, we will not have the intelligent method to remove tokens. Later on, when we incorporate the information calculated in the earlier layers, then our token removal will be informed. So our accuracy will be better than random token removal. Therefore, using random removal is a conservative estimate of the accuracy. Then our method basically is a trade-off between the utility of accuracy as well as the utility of latency. We have a tuning parameter called alpha that determines whether we want to put more emphasis on accuracy or more emphasis on latency. Our method has a very promising result. We advance the Pareto curve. So let me explain what this figure means. On the horizontal axis is the latency, on the vertical axis is the accuracy. The ideal scenario is we want to be on the lower, on the left upper part. The left part means we have a lower latency. The upper part means we have high accuracy. As we can see in this example, we compare our method with several other methods. In particular, the token merge called TOMI. When we tune our parameters alpha, we can push the latency much lower while maintaining the accuracy. And the number here is we can increase, we can reduce latency to much lower. For example, compared with TOMI, we can reduce latency by about 15%. And while our accuracy is also maintained almost unchanged until alpha becomes 0.9. As I explained in the previous slide, alpha is a pure parameter to determine the trade-off between accuracy and latency. Also, we designed our method to remove tokens early. The reason is the following. If we remove tokens early, then we can reduce the computation in later layers. Some other methods, for example, token merge, will remove tokens gradually, even though they may remove more tokens. But since they don't remove tokens early, their latency will actually increase. And while their accuracy may be better, but our method is a good trade-off between accuracy and the lower latency. As you can see, our method will remove 69 tokens from the very beginning, and our accuracy can achieve almost 79%. And our method can reduce latency by 9%. The method we compare with is called the token merge. They will gradually remove tokens, and at the end, they will remove 70 tokens. Their accuracy is slightly higher, 79.5%, but their overhead for removing latency will actually increase the total latency. So as a result, our method is a good trade-off between accuracy and latency. So in conclusion, for similar latency, we can achieve better accuracy. For better latency, we can still achieve pretty high accuracy. To understand our method has some limitations. Our method is designed for small workload size because we designed for 80 devices. And our method also is compatible with decoding-only architectures. Now let me move to a different kind of a method. It's a region transformer adding the Turing machine concept. The concept here is we want to add memory to region transformer. Earlier, we want to remove tokens, but we noticed that the removing token may have an impact on the accuracy. Accuracy may degrade. So what we want to do here is we want to get the best for both. We want to reduce latency while maintaining accuracy, or maybe in some cases improve accuracy. So this is a concept. We actually borrowed a concept from a paper published quite a while ago called the neural Turing machine. If you are familiar with a traditional Turing machine, the Turing machine has a controller that is a finite state machine, and the Turing machine has a tape that's read-write tape. The neural Turing machine here is to replace the controller by a neural network. Therefore, the structure is similar, but the controller has been replaced. So the concept here is we will add the memory to the Turing machine, and we hope we can get the best for both accuracy and latency. So we added memory for different layers. This shows the 2 layers of the Turing machine. We adopted this method, and previous work has shown that this architecture can outperform other methods, in particular recurrent neural network. So what is the advantage of doing this? Our method, existing method for neural Turing machines usually focus on sequential input, such as language models, but we are adapting this architecture for non-sequential inputs, such as images, segmentation, or classification. We want to use this architecture to be faster because we can prove more tokens, but we also have a memory that can allow us to recover the accuracy. I will show you a picture in next slide. This method can also be used for encoder-decoder architecture, and it's more general. So now I explain how this will work. The traditional transformer will be on the right side. So we have a processing embedding. Then basically the processing will go through these layers and computation. We want to reduce the number of tokens to reduce computation. But at the same time, we also want to have more tokens on the memory so that if necessary, we can recover the accuracy by using the memory. The challenge is here, how do we design the read and write blocks so that we can retrieve the tokens if they can help us recover the accuracy. The concept here is we want to reduce the processing by reducing tokens, but we also want to keep the tokens in the memory by creating these read-write modules so we can recover accuracy. And the concept here is the number of tokens for the processing will be smaller than the number of tokens maintained in the memory. We have tried a variety of combination. Our current method, the ratio between processing token and the memory token is approximately 1:4. We find that's a very good trade-off between the 2 streams of data. We have our preliminary result shows that this method is pretty promising. We have tried this on embedded system, JSON O-ring. It has 32 GB memory, and we use image 1K as our data set. And then we compare our method with the VIT small as a baseline and our method. As you can see here, we can actually improve the accuracy by about 2%, and we also can reduce the latency by 50%. So this is a very promising result. We are currently expanding our method to other type of tasks, including segmentation and so on. So in conclusion, we apply neural network Turing machine to non-sequential tasks. Our results show that we can improve the accuracy by 2% and reduce latency by 52%. And we think our method will be applicable to many other existing architectures, including token drawing. The challenge here is we need to train the module for read and write to retrieve the data from memory. Currently, we are evaluating our method for semantic segmentation, and also we are expanding our method to large models. I want to show you this compared with the method presented by previous speakers. Our methods are more recent. Therefore, we have fewer data to present, but I think that will be a good thing for later discussion. So these are some references we use as an inspiration of our method. Thank you. It's my presentation.
Thank you, Professor Yung-hsiang Lu, for your enlightening presentation. And we have got two questions from the audience. The first question is, what is the trade-off between the token removal layer and the accuracy? Will pruning tokens in the early layers degrade the accuracy drastically?
Yes, okay, so the question is, what's the relationship between token removal and the layer we remove the tokens? Is that right?
The token removal layer and the accuracy. The relationship between the token removal layer and the accuracy.
Right. Okay, so the general concept is the following. If you remove token early, you can reduce latency more. But if you remove token too early, then the accuracy will degrade. So it's a trade-off that you want to remove token later because you have more information which tokens you can remove, but the latency will not reduce much. So that's a trade-off here. You want to remove token early, but you don't want to lose too much accuracy. Therefore, that's a trade-off. Does that answer the question?
Yes, I think that's the question. I think for vision classification task, sometimes this task relies on the background, the relationship between the foreground and background. For example, if the object background is sky or trees, you may classify this as a bird. But if the background is lake or sea, you may classify as a bird. So I'm not sure if it's possible to keep some information about both background and the foreground. Maybe the accuracy will be better. If there are ways, yeah.
Right. Yeah, I think what you are saying is exactly right. Depends on the task, right? We based on the data set. So the data set tells us, in this case, we care about the bird, so we don't care about the sky. So we can remove the patches for the sky. That's this example. And then we can look at another example I showed earlier. I think the Statue of Liberty. Again, we consider the Statue of Liberty is an object of interest. Then we could remove that the background here. So it depends on the training data as well. That basically depends on the data set.
I see. So you mean the algorithm is not only removing the background, but it actually depends on the data set, right?
Yes.
Okay, that makes sense. So another question we received here is, what is the advantage of doing token pruning at the hardware level instead of software algorithm level? Are there any trade-offs?
Okay, thank you for the question. The question is, why do we consider hardware? We consider hardware, for example, in this case, if we don't consider hardware, then we may prune the number of tokens just on a higher level. But if we prune one more, then the latency can drop dramatically. So we wish we could push that further to after this dramatic reduction of latency. That's why we need to consider hardware. And this is observed in many different kind of hardware, this phenomenon. So that's why we want to consider hardware, because the relationship is not a linear relationship.
Okay, so another question is, what's the limitation of this work?
Yes, okay. So the limitation of this work is we design for the edge devices, and edge devices usually have a small batch size. So we have observed that if your batch size is very large, so going back to the previous curve here, if the batch size is very large, then this curve becomes more like linear, because we can keep the hardware busy. That's the limitation based on the workload. Why do we consider small batch size? Again, based on what the application you may have. Let me go back to the example I showed earlier. Let's consider this. Let's say this is a robot that will remove weed. So as the robot move forward, it will probably take a picture of some kind of plane and recognize is it width or is it crop. Then you will remove or not. So basically, that is a very small batch size. They probably take one picture at a time and process that. And then if you consider another example is, let's say you're doing inventory management, you probably will take a picture of a product and recognize the product, and then move on to the next product. So that's our justification why we want to use small batch size. As I mentioned, if the batch size is large, then this curve will more look like linear instead of this big drop.
I see. This is quite interesting. Hopefully this work will get accepted.
Thank you.
Thank you, Professor Yung-hsiang Lu. And next, I have the pleasure of introducing our next speaker, Professor Ling Liu from Georgia Institute of Technology. Professor Ling Liu is a full professor in the College of Computing at the Georgia Institute of Technology and an elected IEEE Fellow. She directs the research programs in Distributed Data Intensive System Lab. Her current research interests are centered on data and intelligence-powered computing, such as artificial intelligence, machine learning, knowledge discovery, and data mining, big data systems, and analytics. Professor Liu has published over 300 international journal and conference articles with high citations at Google Scholar. Her research group has been a recipient of the Best Paper Award from numerous top venues. Today, she will share her research on research-efficient fine-tuning of pre-trained large models. Welcome, Professor Ling Liu. Please go ahead.
Thank you, Govan. And also, it's a pleasure to hear the four speakers, including Govan, to talk about the efficient AI work at Cisco and done by other colleagues. Today, I'm going to talk about our recent work that is actually supported as a joint work with my students and also partial funding support from Cisco, IBM, and NSF. And so I'm going to talk a little bit on fine-tuning of pre-trained large models, including language model, vision model, and why they are important, and what are the type of category techniques, what are the issues. And I will focus on resource-efficient fine-tuning. And the techniques I'm talking about probably is different than the other speakers, but I think they are complementary alternative solutions could be all useful. And then I will also talk about some of the open challenges that I see in this landscape. So if you look at a foundation models, whether it's a foundation model for language or foundation model for vision or foundation model for cross-model data, basically there are a number of things that are in common. So most of the foundation model are trained on huge amount of data and with larger parameters. And the more data we train, the larger number of parameters we use, the model has a better generalization performance. And most of the foundation model, when they deployed to a real application like ChatGPT, Sora, GPT, they all basically fine-tune on certain type of kind of a general trend. And if you look at the reported literature, it doesn't matter what models, they all basically list a large number of a public domain data they actually collect the training data from. And then the number of parameters, number of tokens they use, they are huge. The larger it is, the better a generalization performance. So now, what are the issues here? Basically, for this kind of a huge model and trained on massive amount of data, there are a number of issues that are common, and most people talk about these type of limitations. And one of the limitations that are most directly related with fine-tuning is this kind of large a foundation models. Basically, they are not very good when the user's interest is on the specificity, and the specificity is more important than the generalized output. For example, if a particular organization HR policy tailored to specific employees or specific group of employees, and for those kind of policies, they may not be accurately addressed with the generalized a large language model-based AI systems, because they tend towards generic responses. So therefore, naturally, then with a high quality domain-specific information, fine-tuning becomes very important. And there are also other type of techniques like problems that fine-tuning can be very useful. For example, the large models are trained on the data before the training by certain date. Then all the data that are actually produced and after those data may not be incorporated. So therefore, if you just directly use those models, you may suffer from compromise the performance and accuracy. And of course, to retrain those large models is very prohibitively expensive in terms of cost and energy. And of course, the hallucination and the explainability, and when the model cannot have an answer, they present false information. Those are all issues. Therefore, one of the way to mitigate such type of problems is through fine-tuning. Now, fine-tuning today has a number of attractive features. First is when you fine-tune a pre-trained model, you basically utilize the model on a downstreaming task and data set without have to retrain the full model from scratch. That's very attractive. And for a number of reasons, because if you are using a prior to data or privacy sensitive data, then you don't want to provide your fine-tuned data to a large company who have produced those foundation models. So therefore, there are many advantages for fine-tuning and with more efficient resources. So technical challenge for fine-tuning obviously is how to reduce amount of a resource constraint and allows organizations that does not have those massive resources to be able to fine-tune on their own domain-specific proprietary data. And there are also other type of challenges in terms of if you don't have sufficient training data for fine-tuning, and what do you do? And what are the problems? How do we handle the hallucination problems induced by misinformation, skewed data distribution, and biases? And the security privacy of fine-tuning workflows. And these are all common problems. So I'm going to just talk about our research on the first problem. So how to reduce the GPU memory footprint. So if you look at most of the GPU usage for each parameter, basically you can kind of add it up to about 22 bytes per parameter based on the weight size, the optimizer state size, gradient size, activation states. So if your fine-tuned model is IP32 and takes about 11 billions parameters, which is only 15% of the 70 billion models, and you still need about 240 gigabytes of GPUs. So it's still huge. So the whole idea here is parameter efficient fine-tuning is you do not want to use the full model to actually add the fine-tuned parameter size. You want to make the fine-tuned parameter to be smaller, to be a smaller than original model parameter size. In that way, then your fine-tuned part would be much smaller. So that's a general idea. So there are three family of techniques that people are using today in practice. So pruning is one approach, which typically you use either structured pruning or unstructured pruning. But the principle is basically use less data, use less a memory for each parameter, or using less parameter. In an unstructured pruning, like a quantization type, basically you basically sparsifies the weight by masking certain individual weight that are low value, and or you use a structured pruning. Basically, you remove certain weight in groups, and certain group of weight you want to remove them because they're less important. So you assign the importance score on that. Now, if you look at an adapter-based solution like LoRa, represented LoRa family, basically you inject a bottleneck adapter modules inside the transformer block, and then you freeze the model weight and only update adapter weight during the fine-tuning process. So the advantage of this is you don't need to load optimizer state and the stored gradients. However, you still have to load the model weight. You still have to load that. And you still have to compute the activation of the full model. You have to do the backward passes of most operations. And the memory latency overhead is still about 30% of the full size model. And for the quantization-based approach, basically you use less bits to represent each model weight, and the low bit matrix multiplication can be applied. The advantage is you reduce the memory footprint because your weight and activation is cheaper. But you still have to have the optimizer states and the gradients. And those gradients sometimes relies on hardware capacity. And also you actually lost a certain information, and if the outlier weight are actually exist, and like QLoRa is suffering from that. So, and also most of the quantization approach does not take into consideration of the downstreaming fine-tuned data. Therefore, they are not utilizing fine-tuning data. Their accuracy is actually much worse. So what we look at is we're looking at a pruning approach, and we are looking at how the existing fine-tuning approach using pruning to reduce the memory footprint, and then what are the problems, and then we will propose some solutions to mitigate that. So if you look at the pruning and the fine-tuning, so there are two modes that are representing the two family of research. One is a pre-fine-tuning pruning. So means basically in the top, where you inject the task head and to the full model, and then you prune the full model, and then you send the pruned model to the GPU and then to train it on the fine-tuned data. In that case, basically, your pruning part does not using any fine-tuned data. Therefore, you lost a little bit of accuracy because your pruning does not take into consideration of downstreaming a fine-tuned data. Now, post fine-tuning pruning, basically they take the full model, inject the task head into it, then they utilize the fine-tuned data to do a full model fine-tuning first, and then generate a fine-tuned full model, and then they will prune this fine-tuned full model again on the over the fine-tuned data, downstreaming data, and then finally produce a fine-tuned model. So the post fine-tuning pruning is more accurate, but consumes much higher GPU memory. Basically, it's like a fine-tuning a full model, basically. So therefore, the whole idea here is if you have very limited a GPU resources, then the post fine-tuning is not possible to do. Now, how do we actually improve the pre-fine-tuning solution? So whether we could do fine-tuning efficiently and without actually using the full model at the GPU. So that's basically what we are looking at. So the idea is what we propose is to inject to basically iteratively, we still inject the head, but we iteratively prune the full model, basically chunk using a certain group of chunk. And so we do chunk by chunk. So we are not using all the chunks. We are trying to looking at the chunks and then doing the importance-based grouping of the chunks, and then try to actually iteratively learn how to prune the model and without using the full model. And then we load the pruned model to the GPU, and then do the pruned model training over the fine-tuned data. But this process, we do it iteratively. So every time we take a small chunk, small group chunk of a pruned model, and we feed it to the GPU, and we try to run on the fine-tuning. So through this fine-tuning mask-based solution. So this approach basically allows us to utilize a CPU on low frequency, low cost operation that requires full access to the full model. And then we decide which weight to prune using Taylor approximation-based importance estimation. And then we decide which weight we are going to feed into the fine-tuned a model on GPU. So that's basically the general idea. And this idea basically gave us very good result. So we actually run both language workload and the vision workload, and compared with the full fine-tuning, using full model to do fine-tuning, which is the best accuracy. And then with only use a hat to do fine-tuning without doing a pruning. And then we do the pre-fine-tuning and with pruning, post-fine-tuning with pruning, and our approach. So as you can see here, that basically our approach actually very closely approximate the post-fine-tuning accuracy, but we are using a much less. And incorporate the movement pruning-based approach. Similarly, we are using much less a GPU memory. So, and if you look at the breakdown of the CPU usage, and also different deep neural network parameter phases in terms of weight, gradients, optimization states, activation. So you can see the overhead is also shows that our approach using more CPU compared to the other approach. And then our GPU footprint is reduced. And at the same time, if you look at the weight, the gradient, optimization state, activation, we are smaller. Especially we are cutting down significantly the gradient and the optimization states in our approach. And the tunable parameter for our recap is basically the pruning threshold and the masking threshold, because we use random masking to learn what chunk is important. So we calculate the chunks using random masking and to calculate the importance of those group of chunks. This is a vision model, a result. Similarly, we get a really similar result. Basically, we are basically able to leveraging a CPU to do some cheaper operations on the full model, and then select the important chunks to send it to the GPU to do the fine-tuning over the fine-tuned data. Okay, so So this is basically a part of our research. And we are also looking at the cases where when you have insufficient training data, you only have a few examples, then your fine-tuning may not be working. Because fine-tuning, even though you don't need a lot of data, you still need sufficient high-quality data in order to train a fine-tuned model. And so if you don't have those data, or if you also have a hallucination problem and a security privacy problem, then another interesting optimization can be combined with fine-tuning would be prompt engineering. Now, in addition to doing a one-shot, a few-shot chain of thought based prompting, and recently it's a very hot topic would be retrieval augmented generation, a rake-based prompting. So it doesn't matter what prompting we use. In general, we are basically looking at using a pre-trained large model. We do inference on task-specific inference. And then for task-specific inference, we need to actually generating the prompt, generating the query, generate the context. So the limitation, the challenge with that is basically large pre-trained model has a limited context size. And also the large pre-trained model, the inference is still expensive. But this is basically the reality we all face with this. And I want to mention a little bit on the rake architecture. Basically, retrieval augmented architecture can be used for both large language model, large vision model, and large cross-model model. Doesn't matter what foundation model you have, we do need this type of capability, which is the ability to utilize combine the retrieval techniques to retrieve the text data, additional text data from the knowledge source, additional image data from knowledge source, additional cross-model source. And those are not being used in the training, but we can leverage those retrieved data and then to enhance the language model's output quality. So that's basically the kind of idea. So the red box here, obviously, is a retrieval component. So we incorporate into it. Today, this vector database and utilizing the external knowledge and collect them into a vector database. So therefore, when you have a large language model or large model, vision model, or large cross-model model based a request, then in addition to generate a request prompt, you can also generate a retrieval context. And that way you are able to enhance the language model's output, even mitigate the hallucination issues. So that's basically kind of interesting angle. But this area still is very experimental, empirical, because there's not very good generic tools. It's a case-by-case, task-by-task, problem-by-problem based RAG. Here's one example that I really like to illustrate why RAG can be very attractive. So the prompt here is how did the US state guess their names? And it's not easy a answer. So basically, one approach is using using self-retrieval to retrieve all the information. This can be done in parallel. So once you retrieve a lot of information, then you need to do a ranking, a comparison to actually prune out certain chunks and getting the high top ranked result. And then once you have those results, you can add those results as context. In addition to your prompt and a query, you add the context. And then you continuously generating the output. And then you actually critique the output again and select the best segment as your final answer. So these are very easy to understand, but illustrate what is going on with the prompt engineering, advanced prompt engineering techniques. And then I want to mention a little bit of how this tool can be combined. If you look at a pre-trained large model, doesn't matter large language, large vision, just the large language model has a lot more research today. And then if you have a fine tuning on the downstreaming task with the downstreaming data, you generate a fine-tuned model. And then if your fine-tuned model can also be combined with the rig approach that leveraging the external knowledge to enhance your fine-tuned data's output, then you are actually can generate an even better fine-tuned model. Because using this embedding model, using this rig approach, you can mitigate hallucination. You can mitigate inconsistency that your fine-tuned data may not be able to actually completely mitigate. So we had done some work in one of the AI agent experiment. So in here, we are basically looking at using large language model as the entry point, and then to actually develop a AI agent that can battle with the human players. And we call it Pocky LLM, which is playing Pokemon game. And in this system, basically, we combine the rig approach. So we build a Pokemon game, a knowledge database, vector database, basically utilizing the retrieval capability. And then we also utilizing the model fine-tuning over the large language model. And we combine them and to actually mitigate the hallucination from the large language model as a foundation model we use. And also we use that to mitigate the inconsistency in this rig and the large language model based combo. And when the game, the action is generated is inconsistent, then we actually we critique our solution and revise our solution. So this basically shows there is some interesting way to use advanced techniques to continue enhance the fine-tuning capability. So that's also one of the attractive solutions. And to conclude, basically what I want to say is that resource-efficient fine-tuning, advanced prompt engineering, and retrieval augmented generation, reinforcement learning, these are all very good techniques can be jointly developed to make the efficient AI, to make them as efficient AI solutions. Now, what are the open problems in this domain? Basically, in addition to GPU memory efficient fine-tuning, and there are also a number of things. One is if the data and fine-tuning data can only be collected over a population of client, edge client, then centralized fine-tuning would no longer be possible. Therefore, federated learning, federated fine-tuning becomes a very important direction. And those fine-tuning needs to be not only computationally efficient, but also communication efficient. And in addition, when you are doing fine-tuning, and the entire fine-tuning data, fine-tuning workflow has to be also safeguarded for security privacy threat, and including a Trojan, data Trojan, model Trojan, and privacy leak, these kind of issues. And finally, actually fine-tuning also needed to be robust against the hallucination-induced safety issues. And those are not even related with privacy and security threat, but also related with a data skewness cause problem, misinformation cause problem, biases cause problem. So those are very challenging problems. Finally, still, how do we use fine-tuning to actually increase the explainability of the foundation models in terms of reasoning, in terms of output? That's also a very interesting problem area that I believe that we're study. And that's also should be basically efficient AI should also be responsible, should be also guarantee both high performance and safety. I think that's all For me, I think the time is just 25 minutes. Thank you. So this work is basically, this is my collaborator, okay? My student and a Cisco collaborator, IBM collaborator, so I'm putting them here. Thank you.
Thank you, Professor Ling Liu. This is really great work. And we have a couple of questions. The Pokemon work looks very interesting. The agent behaves like a human to play with the computer. Is that the work? Is it possible to play in real time? I mean, for that work.
Yes, actually, because a Pokemon game is basically is not time sensitive. However, the agent is playing in real time with the human player. So basically, the agent we wrote has capability to play a low level or medium level player. But when we play with the expert player that are top performers, then we still lose. We're not winning majority of the battles. The reason is, I think the knowledge we use to program the AI agent does not have the expert knowledge yet. So what we are looking at is maybe we would play with expert more, and also build more soft play so that we could learn what are the tricks that expert plays in order to enhance the model. It's in a similar way like the AlphaGo, right? AlphaGo play the expert first and then soft play in order to learn a lot of tricks. So what we see is that there are a lot of tricks we are not, when we are writing the code, we're not able to capture those. And there are tricks that a Pokemon human expert that are really good at it. Because the student who actually play that is a medium player. And even my daughter is a medium player. They are not an expert player. So expert player has some tricks that needs to be learned.
Yes, and that's really interesting. And is it possible to generalize this method to other games?
Right, it is possible. So currently our framework is actually can be generalized to actually playing different type of games, and even doing certain kind of planning, travel planning, things like that. So it's just the student still working on how to make the benchmark, to develop a benchmark using the Pokemon game as a benchmark to testing this type of AI action agent, and using language model as the entry point, and then to access different kind of external knowledge, and in order to actually, because the entire framework is generic, but we can use Pokemon as a benchmark, so people can test their AI agent using Pokemon game as benchmarks to evaluate that. So that's what we are looking at right now.
I'm looking forward to your new work on the Mark. And we have another question. I think it's related with the first part of your presentation. Why do you prefer structured pruning?
Yeah, okay, this is actually a good question. So the main idea with structured pruning is because structured pruning is during the learning, during the learning process, you also pruning. You prune not in a fixed fashion, because a quantization-based structure, unstructured pruning, you do not look at the fine-tuned data. All you do is take the original model and then try to prune out those low ranked parameters, and so therefore you can reduce the size. But when you are doing fine-tuning, the fine-tuned data is high quality data. Therefore, utilizing the high quality fine-tuned data to do pruning, it would make the pruning more effective for the downstreaming task that you are trained for. So that's one of the main reasons that we believe structured pruning allows us to work with the fine-tuned data in an iterative fashion is more important. So that's why the reason pre-fine-tuning with pruning is failing is because they don't use fine-tuned data. So if we want to do pruning and fine-tuning, we should both using the fine-tuned data to leveraging that high-quality data in order to make the pruning more efficient.
That makes a lot of sense. And thank you, Dr. Ling. And I think now we have heard from our esteemed speakers. Let's move into our roundtable discussion phase. Please turn on your camera if you can. Welcome to the round discussion session. And the first question we care about is how can Cisco Research improve its support for universities or strengthen our collaborations? We'll go first.
I can say.
Yeah, please go ahead.
Basically, my experience with Cisco University Research Organization has been very, very good because I believe that Cisco a research, especially the University Research Organization, is one of the leaders in this promoting industry academic research collaboration. And even in the recent economic recession period, Cisco Research did not shut down its industry academic research collaboration program, where some other company I don't want to name for, but they actually were not able to continue. They temporarily shut down for a year, for example. And another thing I really want to mention is that I find that the interaction and the discussion frequently with the Cisco researchers also very rewarding for reassuring the academic researchers, our PhD students, that their choice of problems, their choice of solutions are practical, are relevant. So I would like Cisco University Research to continue this angle of support for this kind of, continue to be the leader in this area.
Thank you. We hope we can support as much as we can. And I think maybe Elisa.
Maybe I can say, maybe I can say a few words. Also, our collaboration was very positive. Also, the students were excited, and as long as young people are excited, that's very important, for us to support the young generation. So I guess. Eventually one possibility will be also to foster some kind of internship or something that will be, also important for the students. And so eventually, I don't know if more of this opportunity can be considered for the future. So overall, also this area of efficiency, as you show clearly in your slides at the beginning of this event, it's clearly a key area at this point, and you mentioned the paper on unlearning that are growing, the paper on pruning that they are growing. So definitely there is a strong interest, and so I think this collaboration it's very important for us in academia.
Yeah, we hope we can have more intern opportunity and positions in the future. We will give feedback to my boss and maybe the executive if there are budget for more interns. Thank you, Elisa. And Yung-hsiang, I see you.
I can comment. Sorry, you talk first.
You're on mute. You're ready to say something.
Okay. First, I want to thank Cisco's support. I want to thank Gaowen and many of your colleagues. We had several discussions over the year. Give students very good feedback. That's really truly wonderful. I also want to echo what the two previous speakers said about interaction. So it's good opportunity. One possible thing maybe is to have a better understanding of the problems Cisco wants to solve. I think we are more like academic research and if it's possible, to have a more understanding about the problem Cisco wants to solve, and maybe we can have a better collaboration and more impact on technology transfer.
Yeah, I think that's a great suggestion. And we see from this year, from industry and academia, everything is changing every day, and the priority sometimes we may shift the priority a little bit. It still takes some time for us to figure out what's the most important problem. I think we can definitely find something we can collaborate on together.
Thank you.
Yeah.
Okay. Yes, sure. I can also add a few of my thoughts. I agree with what previous speaker said. I think the current collaboration between academia and Cisco Research is very successful. The ModelSmith as one example, right? That's gathers research outcomes through the collaboration, and Cisco is trying to lead open source benchmark for the community. That's very good. And I think this is a mode should be further promoted, right? So think about what's the strength of academia. I think the research ideas is the strength of the academia. So we have very good students, we have very good the faculties. We always have some ideas, but what's the limitation of the academia and resources, right? For example, we do publications. We do publication a lot, as you show in our slides, right? But I think the disadvantage from academia is we typically are not that good at, for example, building the benchmark and, for example, UI. Design, right? But this could be a strength of the industry. Industry has a very good team for software engineers and building the benchmark and the UI stuff. I think that could be some potential collaboration that further built between academia and Cisco Research, and we can make a more impactful product, not just a product for the Cisco Research, but it could be a product for the whole community. Yeah.
Yeah, I totally agree. I think industry is a little different from academia. We can't assume all customers have knowledge in this area. So we hope we can build some user-friendly UI to let different users with different level of technology background can use these tools, and they don't need to understand the details of the technology, and they can still use our toolbox such as ModelSmith. That's our target. And come back to our main topic today. So in terms of efficiency, such as memory model and data efficiency, and considering the stages like training and fine-tuning, which efficiency type does your team lean towards, and what are the reasons guiding your preference?
Maybe I can go first. I don't know if we go in the order of no. So there was something that I didn't show in my presentation that I like also to put forward. I mean, I definitely presented a couple of works that were related, to really reducing, improving efficiency with respect to handling with multiple tasks. But then there is something where where we be working on that is like combining pre-trained model and having training-free approach. I know that a large part of the community is doing that, but I saw at CVPR some works are related, to almost training-free or test time adaptation methods, or without requiring to entirely retrain the models, and that I think this is also something where I think still the community can push a bit more. So this is also something that we are doing.
Yes, I totally agree. I see a lot of work these days, training-free or something like data-free. I think that's because the models are too large, and it's difficult for small groups to train, work on something related with training. And Ling, I think you raise your hands. It's your
Yeah. So for me, basically, even Zeroth has a lot of A100 GPUs to reserve those, and it's very difficult also. So basically, to training a large model like OpenAI, like Facebook, Google does, we don't have the resources. And we cannot even reserve it. Even the total resource may be more, but each student each time can only reserve a few of them. And 10 GPU at one time is already significant a success in getting hold of those. So it's kind of hard. So that's why fine tuning becomes a feasible research possibility for academic, especially for university, for students who are able to get a hold of the resources. And also I believe that the reason that the large company with large resources can actually put up this type of foundation models is also a trend, just like search engine. How many company can run search engine? Very few. But how many people utilize search engine and optimize search engine? Many. So this kind of foundation model going to be a trend, going to be produced by large companies, even including in the future, the foundational cross-model model will be produced by OpenAI and Facebook, this kind of thing, like OpenAI GPT-O is already like a AI Sora. This kind of big model would be produced by them. But how do you fine-tuning those to for a problem-specific, task-specific jobs, and for a privacy proprietary sensitive data that you don't even want to send a query over them. So that are basically a very important research topic, and especially in the future, if there is a foundational model for material science, foundation model for a particular healthcare domain, then there are many privacy, proprietary data that requires a fine-tuning. So that's why I believe fine-tuning is a great area for academic research.
Yeah, I totally agree. I see there are a lot of work in this direction come out, and it's difficult for academia to train any foundation models, I believe.
Right. I think the same observation. I think that's what we try to do there is to use existing work instead of trying to train from scratch. I think most organizations don't have the resources to start from scratch.
Yeah, I think so.
Yeah, I can also add a few additional points. I think efficiency is a quite broad topic, right? It requires understanding data model interactions. I give one example. For example, in our today's talk, I think Elisa mentioned design a once for all pruning mask, right? And Ling talk about fine-tuning specific pruning mask, right? This is efficient. Typically, it's user defined, right? What kind of efficiency, desirable outcome that we really want? That's task by task. But one interesting point is about the efficiency. I think it's the typically why we care efficiency is not just about the resource limitations, so on and so forth. I think this is also relevant to the very general scope, which is called model personalization. So for the research like in academia and also many research in industry, you have the pre-trained model already from the open source, for example, from using Llama, so on and so forth. But most important thing you are doing is model personalization. But when you do the personalized model, typically you don't have to test the full model, right? Because the large language models has a certain characteristic which is called modularity. You need to understand the modular component within large foundation models. And since you are personalize this model for very downstream specific task, you should understand, okay, where you should touch and where you should make the spark, where you should compress, so on and so forth. I think this is a model personalization and efficiency. They are very relevant to tasks and also relevant to, I think what Ling mentioned earlier as well is efficiency is not alone, right? It also relates to other metrics like robustness, hallucination, privacy, so on and so forth. Yeah, that's a very broad topic. Yeah, many interesting questions you made.
Yeah, Yes, I totally agree with what you said. And when we are achieving the accuracy, we may compromise other properties like efficiency, like the safety, robustness, and accuracy. So is there a way to balance these metrics?
I would say we should look at the application and understand the need of the application. Then we have a better understanding what is really needed. Some applications, I think we mentioned earlier, the timing requirement is very, very important. So in that case, a response time maybe as important as accuracy, but some others maybe accuracy is more important than latency. So it depends on the applications.
Yeah, I think so too. And Sijia, you have something to?
Yeah, I think some metrics, their interrelationship could be very complex. Some metrics are co-promoted. For example, you are pruning something, but actually you are not sacrificing. I give one example, accuracy. At least for the image classification, that's what lottery-ticket hypothesis tells us, right? But some metrics are conflicting with each other. Another example is the robustness versus accuracy. And robustness and accuracy is a trade-off. And another metric is called privacy. If you look into privacy versus sparsity or pruning, they are also not conflicting with each other. Pruning somehow also preserves privacy. So therefore, interrelationship across the different metrics are different. For sure, they are task specific, but there is a very fundamental limit of the different metrics for those models. I think they're very interesting fundamental questions to understand their interrelationships. For some conflicting metrics, for sure, we should use more advanced algorithm to achieve the best trade-off, for example, multi-objective alternation, so on and so forth. But for some co-promoting metrics, maybe you can optimize one and achieve another one. I think their relationships are different at different levels.
Yeah, I see Professor Ling, you raise your hands. You want?
I just want to add a little bit on this thing. So basically, today when we do research, when we are looking at efficient fine-tuning, most people focus on preserving accuracy or sacrificing less accuracy and with minimum a GPU memory footprint or efficient communication a bandwidth. But if the efficient AI would also include not only the performance as metrics, but also safety as another metrics, then it would stimulate researchers to measure the solution approach with those safety metrics as one or two criteria. Just like the previous speaker says, that basically some of the metrics are conflicting, other metrics may not, and the privacy preserving a solution may not guarantee a security Trojan problems. So there are many issues in here. It's just most of the study that so far has been focused on one matrix, two matrix, that's it. So there is a need to have a holistic study on defining what is the absolutely practically usable efficient AI. Then it would probably.
I totally agree with what you are saying, and actually, I do believe that maybe one issue is that the community of people studying safety, robustness, efficiency have been totally disconnected. So I think, for instance, the possibility to organize joint events to foster this thing would be definitely useful to analyze this phenomena in a holistic manner that is at the moment clearly lacking.
Yeah.
I agree. It's different case by case, and depends on the use case. You should define which metric you care most. And another hot topic is the vision language model. I see everyone mentioned this vision multimodal models, and what are the specific challenge when addressing the efficiency in vision language model.
Let me say something. Then I'll just say something in the silence. So I have done some work in the past on cross-model learning. So what I see is that in this cross-modality based domain, multi-model domain, still we would need a real good foundation model where they can generate they can train on large amount of a cross-model data, and then actually with a lot of parameters that covers the excellent generalizable embeddings, cross-embedding models. Then again, we still have to train those foundation model with specific task. For example, if you want Sora to tailored for particular type of movie with particular type of story, then you need to fine-tune that. So that's why I believe this trend, large language model trend, it would apply to a cross-model domain as well. It just right now there's not the area of generating large foundation model for cross-modality learning is still just starting. So OpenAI has a GPT-4.0, but we don't have a lot of competitors. But I believe that is one thing. I also believe fine-tuning with retrieval augmented generation is still important because there are so many vision data, vision model that can be leveraged through this retrieval augmented generation process, not only to do the retrieval on the knowledge, but also retrieval on the pre-trained model that has been done before that are excellent in utilizing in being utilized, which is exactly Sora Hugging GPT they are doing, right? They are doing not only data, but they are also doing model selection in order to provide a better answer, better output. So that's, I believe, it's going to be a trend.
Yeah, I totally agree. The new versions of ChatGPT, multimodal models, and also the new version of Gemini, multimodality model, I think there are a lot of work to do in this direction.
Yeah.
Anyone want to add something?
Yeah, I can add a few things as well. I think for the multimodality, if we talk about vision language models, vision modality and language modality, these are two most common modalities we consider right now. But there are also other modalities people want to include, for example, speech and acoustics, and also tabular data and graph. So that's just if we consider incorporate different modalities. In fact, I think one important question for us, we should think about how those modalities complementary and conflict with each other. I give one example for the vision modality and text modality. In fact, they could help with each other. And if we think about the current vision language models and the vision encoder, typically we copy from the CLIP model, right? And but if you do some hallucination testing or robust testing, and you test a vision language model and then compare with large language model, which is just without vision component, surprisingly we found that vision language model is more robust. So I think this additional modality of benefit coming from perspective. So therefore, how they could interact with each other for cross different modalities, that's a very interesting question. I don't think their role will be the same. They could be very different. Yeah.
Yeah, I agree. It's a challenging task, and we can continue the discussion further offline. And we are on top of the hour. I think we need to end our discussion. I want to extend our sincere thanks to our panelists, Dr. Ling Liu, Dr. Elisa, and Dr. Lu, and Dr. Sijia Liu for sharing their expertise and perspective with us today. And let's continue this conversation beyond today. Feel free to reach out to our panelists or connect with us for further insights. Thank you as well to our audience, and thank everyone once again for joining us. Have a wonderful rest of your day. Thank you, everyone.